to eat fast, but to talk. And then at that point, this is what we did. And believe it or not, again, Michele is part of the initiative as member of the advisory board. Then I think this is interesting because this tells you how I felt Michele move into catalysis and how he drove me into the field of catalysis, and then we have this thing running. Okay, this was for a little bit of the introduction, and then let me move to the talk, and I hope I will be able to tell you what I wanted. And it's, there are two concepts in the whole talk that you will see. Many people know that with light and with external stimuli, you can drive systems out of equilibrium, and then you can create new phases of matter. But those new phases of matter has two problems. A, that they are short-lived, are metastable, and they usually you need to pump in order to keep things alive. It's like us, to keep being alive, we have to eat. Then the same thing. It's an out of equilibrium phenomenon. The question open is, can I do the same in equilibrium? Can I map the problem of laser-induced to cavity-induced? And I hope during the talk will become clear that the answer is yes, in part. No? And then this is what I want to introduce to you. Then, jumping, I will tell you what is the difficulty, and this is the concept of polaritonic chemistry or catalysis. This is a general problem. You don't need to have cavities to realize that it's very complex. You have to address with electron motion, nuclear motion, solvent organization, then reactivity itself, and then we are adding something new, which is the fluctuations of the electromagnetic environment. That could be real or the vacuum quantum fluctuations. Okay? It could be driven or vacuum. And I want to address the second case, in which you have the fluctuations of the vacuum field. And then basically this is where it comes into play that we have this setup of cavity quantum electrodynamics. That is not a new topic because in atomic physics it's been used for many years in atoms, and there's been 4 Nobel Prizes just on cavity things, but on atoms, then with no relevance for what is chemistry and solid-state physics. Okay. Then basically let me guide you why this could be interesting, and I hope this is a cartoon which is too simplistic, but illustrates the idea. You've been discussing the whole conference about the formation of bonds and breaking bonds to create catalysis. And this, the typical example, you have the hydrogen the atom, and then you form the hydrogen 2, which is the bonding and anti-bonding state. And everybody will know that H2 is completely different to H. No? Then if we do the same, now, instead with another hydrogen, we do it with a photon. This is a cartoon, don't take it too seriously. What you can form is a light-matter hybrid, which is a linear combination of the electronic excitation and the photon field, no? For a given Q vector. And that's what is a polaron. And then you will have it, the bonding and anti-bonding polarons. Then you can see that if you use that as ingredient, you can now use those polarons to create a new chemist, a new phenomena. Okay? And then eventually the formation of those states has to be different to each of those components. And this is the key, because everybody will tell you that this is not going to work because in perturbation theory, the photon will not change the hydrogen, but the hydrogen with a photon is a different entity than as H2 it is. Okay? And there are many cases that you find that, which is vibropolaritons, which is the coupling of light with phonons, or exciton polaritons, which is the coupling of light with excitons. But you have many, many of those. There are at least 70 types of polaritons that you can use as Lego to build the platform to study materials properties. Okay? Said that, looks interesting, but now I think we have to put numbers, because I think it's important that get things realistic. Those 0-point field effects are usually very small. Not zero, which is really, this is important, because you will see many people that has written no-go theorems claiming that the effect is 0. This is not true. Okay? And then basically you can have the Lamb shift, which is one of the typical cases in which you have the splitting of the 2p and 2s orbitals of the hydrogen atom and the motion of the energy of the atom in air, which gives you the order of magnitude, 10 to the minus 6. It's micro electron volts. It's really minuscule, but still it's non-zero, and this was one of the Nobel Prizes. Then you have another way, which is van der Waals forces, that has been discussed in depth during the conference, and the source is also some kind of quantum fluctuations. And the other typical example is the Casimir forces. Casimir forces is one of those cases which are really interesting, which is the attraction between plates due to the modification of the vacuum field inside. And it's important because it's a non-perturbative and you have to do the summation over all states. It's one of those things for those of you that are mathematical in nature that is interesting to do it. If you want, just try to do it and you will realize that it's a non-trivial problem to do the summation, because for each cavity mode, the force is repulsive, okay? For each individual. And for the sum of all cavity modes, the force is attractive. And this is connected with the Riemann extension of the Hilbert space. It's really interesting in particle physics. Okay? Fine. The numbers are small, but they are non-zero. And then basically this is what I want to convince you today, that can we use those vacuum fluctuations to control chemistry? This is the only question I will try to address in the whole talk today. But as many things were done, is you can do exactly the same with materials. And materials has an advantage. Quantum phase transitions, when you are very close to phase transition, you just need to kick slightly the material and will undergo the phase transition. And this is what happened in what is basically cavity-induced superconductivity, cavity-induced topology of photoconductivity. And then I just put you here 4 cases, which is ferroelectricity, which was discussed also by Roberto. In the case of STO, you can induce a paramagnetic to ferroelectric transition with the cavity. In STO, all those, the answer that you can do it theoretically is yes. And just recently, in the last weeks, it has been proven experimentally that the superconducting temperature of a normal organic superconductor can be reduced. Sorry, it's not increased, it's reduced, but the cavity does and have an effect. Then it's important. Okay, if you're interested on the materials, I'm happy to discuss. During coffee, I will excuse myself, I will talk about chemistry. Okay, for doing that, as the whole conference was on methods, we need to develop new methods. And then you can see what is the challenge. Everybody has told you about what are the problems of treating electrons and phonons together. And now what we want to add is a new species to the soup of particles, which is the photon. And then the question is how we can do that. And it's a non-trivial case, and then the problem is you want to treat electrons, ions, and photons quantum mechanically. And if you do it with classical equations of motion, you have a problem, because you end up in classical Maxwell equations. The question is, can I do one step beyond in order to include everything at the same footing? And then the idea is very simple, and introduce some of the concepts that I think are important to combine, and I will tell you now. Instead of working in the Coulomb gauge, we are going to work in the temporal gauge. The temporal gauge is one of those gauges that the people in particle physics use a lot. Okay, and I don't know how many of you have asked yourself, I didn't do it, then I know why in the textbooks that we teach of solid-state physics and quantum mechanics, we take the Coulomb gauge and we write a Schrödinger equation stationary. There is no reason to do that, because this is a choice of gauge that you have taken because you want to get the t equal infinity limit of your system. But you could do it as well with time-dependent phenomena, which is a scattering problem. And that's what you do in quantum electrodynamics. You are looking for stationary solutions. Okay. Said that, now you will understand why I'm saying it. Basically, if you just take photons as the mediators of the Coulomb interaction, what happens is you have the 2 particles, and the mediator is emitting a photon, being absorbed, re-emitted. And then this photon absorption and emission is what gives you the Coulomb potential that you know. But you don't need. You just need to have to treat photons. And if you do it that way, the Hamiltonian, interacting Hamiltonian is linear. It's not quadratic. Okay? Then the Schrödinger equation in the time-dependent gauge is linear. This is really important because then you can do all theorems that we know for density matrix which satisfy for linear operators. What is the problem? The problem is, of course, that it's not bound because you have many particles, and it's a scattering problem. And then you don't know how long you have to do the simulation to reach that problem. just to give you flavor, if you do the gauge transformation from that interacting Hamiltonian and you go to the Coulomb gauge, you get the 1 over R12 that you are familiar with. But you get that as the first order term. Because if you look at it, there is no divergence in the Coulomb potential, and there is retardation effects included in the theory. Then this is good, because then some of the problems that we are facing in DFT and quantum mechanics comes from the 1 over R12, which is there, but it's something that we have introduced because we want. We don't need to. We can have another pain, which is to treat a time-dependent problem with infinite variables linearly. Either the two are equivalent. Which one you want to solve is up to you. But you don't need to choose the 1R2. Okay, then basically that's the summary of the equations. Then you get this standard interacting Hamiltonian, which you have the kinetic energy of the electrons and ions. Let's put the longitudinal part in the Hamiltonian, then the photon field, and then the interaction between the photon field and the current, which is the matter current. What is the advantage of this? Is and this I didn't know. First, is the only Hamiltonian that mathematicians has proven has a ground state. Then if you take and you ask them, Consham DFT has a solution, the answer from the mathematicians is they don't know. They cannot prove it has a solution. They cannot prove it does not have a solution. Then either way is open. But for this one, they can prove there is a solution, which is good, is bound, and self-adjoint. Then it's really interesting for this point of view. And then, of course, you can do the density functionalization, and then I will not run you through the derivation because it's too long, but what you need to get home is that the many-body wave function of electrons, photons, and ions is a one-to-one correspondence with the current operator and the gauge field that you choose. And then this tells you that you only need to know these three-body quantities to represent the full dynamics of a many-body interacting system. As every time in DFT, you don't know the functional. We need to get it, but that's a really interesting proof of concept. And then what it entails is that this is a set of self-consistent Maxwell-Consham-like equations that I will show you in a minute how they look like, because I think it's important. Is you have this Hamiltonian in which you have the minimal coupling with an effective gauge field, which comes from the external field plus the internal exchange correlation field from the photons. There is a magnetic field that gives you the splitting and retardation effects, and this goes for the electrons and the ions, and then the coupling between the matter and the fields. And if you write the equation, you have an equation of motion for the current, which is a Schrödinger equation. Yes, I wrote it compact in this way, but this is the normal Schrödinger equation, and this is the second-order representation of Maxwell equations for the transverse part. Okay, then there is nothing else. But the beauty here, and this is something important, Maxwell equations are different to the ones that you have in textbooks, because the A that appear here has components from the matter field. And this is something which is new and has to be included. Now you have a way of choice, which also was done by Roberto Carr and Michele Parinello, is to solve the dynamics making this second-order differential equation, which is your method, or I can take the Maxwell equation and make it as first-order differential equation. I'm not saying this is the right thing to do, but you will see why it might be the right thing to do. If you take the density tensor of the electromagnetic field, which is nothing else than F is E plus B, just write it. Why I take this quantity? Because that quantity by construction is gauge invariant. You do whatever you want, the fields are the real fields. Then if you write an equation of motions for E and B, you don't need to worry about gauge. And that's exactly what happened, because if you take the equations and you just do two lines of work, the equation of motion for the phi, for the F, which is the field, is a linear equation. It's like a Schrödinger equation. Then that's the path that we took. We took a Schrödinger equation for electrons and a Schrödinger equation for the photon field. And there are two linear equations coupled. You could as well have done it with second order as the method of Roberto and Michele. But this at least introduced the gauge in a natural way. Okay? And then the last question you might ask, do we have functionals? Okay? And then the answer, let's take the simplest case. I remove the B field from the equations and I only have an electric field. And what I do is I take a 2D gas and I take quantum Monte Carlo and I solve the 2D gas thread by a quantum field. No? And this can be solved. And then from that you can extract the equivalent of the LDA for photons. That's what we did, and then basically you get that there is a photon LDA, which is proportional to the density, as you might expect, and then you have all the correlations. This is an analytic expression. What is the advantage of this is that photon-photon interaction is very weak. Goes as 1 over c squared, then it's very weak. In contrast to phonon-phonon, which is very strong due to harmonicity, or electron-electron interaction. Then first-order representations of the photon-photon interaction via the matter would work. And in fact, they work extremely well. Then those functionals for the photon sector are much better than the functionals that we have for the electron or the phonon sector. And we were lucky due to the fact that the photons do not interact. Okay, that's the analysis. And then the last thing, and maybe if I run out of time, I don't show you chemistry. I don't know how many of you, this is an old movie, maybe some of you already saw it. You have thought of how an electric field of a photon looks like. Okay? And I'm going to take you one case, which is spontaneous emission. I will take you two cases. Then basically what I take is an atom. I go by hand, I put the first excited state. If I plug that as a t equals 0 initial state, and I do the propagation, the system has to emit a photon and go to the ground state. That photon, if it's bounced back, could be reabsorbed and then excite again. Then the movie of them is this one. Basically, you get the emission of the photon, then you get the Lorentzian shape with the spontaneous emission line width, then the photon will be absorbed. You see the deformation of the line width, and eventually you get to the one that you know. And then the probability of absorption gets reducing proportional to the dipole moment of the atom, which is, if you want, Fermi-Golding rule in real time. And then that's the only thing we are seeing. Of course, the time scale is 1 over c, then it's too fast. But you are seeing that in that time scale, you can modify the shape of the resonance, and then you can control also the probability of absorption. And every time the photon is absorbed, you get another bump in the wave packet propagation. But it's interesting because it's a wave with a sharp transition. This is really interesting for all emissions of light. And this is just how you treat a spontaneous emission in this.
What was the time scale of this decay?
The dipole moment of the, which is basically Fermi-Golding rule, no? If you just translate the Fermi-Golding rule with delta omega minus E, and you put it in time, it's exactly what you say. This is a parameter that you have. But this is only to illustrate. Then now that you saw that, could come the beauty of the theory, because they will allow you to do two aspects. Let me, before running the movies, the top one will be exactly what we did above. And the bottom one will be a completely Gedanken case in which I change by hand the light matter coupling to a very strong value, which is called strong light matter coupling. Okay? The difference here is instead of having 2 levels, I will have a 3-level system. I put the electron here, and the electron will go from here to here and from here to here. This is a parametric down conversion process in which you entangle photons. It's what you use in solid-state physics to get entangled photons. Okay? And then that's what we are going to see. But on top of that, you are going to see something which is really interesting. In the first case, you have the emission. Then all of a sudden, the population of the photon is 0. And then you get that the population of the photon field is 1, get to 1 here. But in the strong coupling case, I don't know now, let's see, you never get to 1. But just check what is happening at the atom position. The electric field is never 0. You never get the full emission of the photon field. This is what I was telling you before. This is the light-matter hybrid state. And if you want, that's what is being used in nonlinear spectroscopy when people talk about slow light in matter. Slow light, when you make light, really basically stopping light, what you are doing is making sort of quasi-bound states of photons in the matter sector. Okay? And this is something to illustrate that if you have a strong light-matter coupling, you do get that. A way to do it is in solids. In atoms, you can do it by artificially increasing the light-matter coupling. Okay, this was for the theory, and then this is what I wanted to show you, how we can control chemical reactions. And then let me just tell you what is the experimental evidence. And the experimental evidence started in 2016. We have the first papers in 2014 predicting all that, in which Thomas Evison showed that the rate of a chemical reaction is being modified by having the reaction in or outside the cavity. Then there are many reactions that has been demonstrated over many years now, and then now there is consensus, finally, that there is an effect, okay? That the effect is non-zero. I just wanted to tell you that at least a big number, I will not put a percentage, but it's very big, of the reactions are not affected. Then it's only a small set of reactions that are affected by the cavity fill, okay? And that's something which is new, and that's what we want to address. Before getting there, let me show you under which conditions you can get modification of the electronic structure of molecules. One thing is that you've been discussing is charge transfer, energy transfer between molecules, donor-acceptor, okay? This donor-acceptor, I will show you the case, is a donor and acceptor molecule, and then if you put donor and acceptor and you move them apart, the energy transfer will be proportional to 1 over the distance cube. Then it's really, immediately, for far distance, the transfer is 0. And this is one problem in biology, that the biology has solved by having multiple centers. But the question is, can we improve that? And there is something interesting. If you think of energy transfer, what you have to put is a conduction channel between the donor and the acceptor that funnels the energy, and then you will have them conduct. You are laughing, but that's exactly what the biologists do with optical fibers in order to increase the length of conductivity. Now our conductor will be the vacuum field of the cavity mode. And then this is the result. If we have a cavity which is resonant with the HOMO-LUMO transition, this is a non-realistic cavity because the HOMO-LUMO is 4 eV, then not possible to do those cavities, but in the computer we could. And then basically what you see is that in normal conditions, the decay rate is proportional to the distance, and then there is the energy transfer decays extremely fast, but the transverse component of the electromagnetic field dominates at large distance and keeps the energy transfer constant, and for distance of over hundreds of nanometers, which is very long. Then if you keep going away, the retardation will take place and then will die. It's not infinite. Then this shows you a case of energy transfer mediated by photon field. The second one, and this is just, I wanted to show you, just that you don't ask me, what about the functionals? And then you can do the same with couple cluster, CC, SDT, and then for the molecules. And then you can couple to the QED and get the electronic structure of, in this case, will be dimer, which is dimer-dimer interaction, which is van der Waals interaction, and in this case is water-water that is being discussed. And then basically the only thing I want you to check is the dash curve with respect to the continuous one, which is in this case is the couple cluster. Result, you see that the binding energy as well as the frequency in both cases is being modified by the coupling to the light matter. And then it's non-zero. Word of caution is I use an artificial 0.1 light matter coupling, which is what you call a strong light matter coupling that is not easy to get experimentally because this is a single molecule. Okay, then we got there. We see that if we have a single molecule in an otherwise bath of photons that are strongly coupled, there is an effect. But nature doesn't work that game because the light matter coupling is weak, as I showed you in the beginning. Then we need to enhance it. And then the trick is that you put many molecules, and then what you do is you look for the transmission of light into this setup. And then basically you get something that is very well known in quantum optics, that there is a Rabi splitting between the lower and upper polariton, and if you increase the number of molecules, the splitting increases with the square root of the number of emitters. This is well known, okay? And that's the trick that is being used to achieve strong collective light matter coupling for many molecules. Now, the open question is how you translate that into chemical reactions. Then basically this is the question that needs to be solved. And we have this light matter coupling that is known, and then the local chemical reaction is local, it's not collective. Then you need to have a way to translate for a short time this collectivity into locality. Okay? And that's what I'm going to try to convince you that we have a theory to do that. And I'm happy to be told is wrong. Okay? Like this is the speculative part of the whole talk. But this is the thing interesting. Let me first tell you that the first part is always true. And then what I'm going to show you is we have a set of thousands of nitrogen molecules, and I do something which is simple. I come with a pulse through the left inside, and I look to the transmission. Okay? But then I will look to the transmission, which is what I showed you before, and this is what you get. You get a Rabi splitting, which is proportional to the number of molecules. Nice. And then you might ask, what happened with the excitation of each individual nitrogen molecule? And then, in fact, what happened is that there is interference and it's being killed in the transmission. However, if you were able to do a spectroscopy on each of the molecules, you will see what I'm plotting here. Here is the Rabi splitting is here, that to that. But the dominant feature in the optical absorption is the normal excitation that you have in the molecule. But it's destructively destroyed when you look to the transmission. Then you don't see it, but it's playing a role. Okay, with that in mind, that's important because this was one of the debates. Then the electronic structure of the molecule is important. This is what is happening. You come with the light in this direction. And then you see that as the light is coming, you start to form this collective electromagnetic field, which look like plasmons. And those are the coupling of the light matter with the molecular system, which will be spatially dependent. Yeah, and then this is in the X or in the Y direction. That's more or less I show you, and then you can see how the electromagnetic field is dissipated, and then you can do the Fourier transformation, and then you get the Rabi split. Okay. So far, we didn't get to chemistry. I hope I get, and then we stop. Now let's look to something. And this is completely new and has never been done, and I don't know why. Okay? And then this is, instead of looking to vibrational strong coupling, why we don't look to something that in chemistry is very useful, which is Frank-Condon transitions. Then what I do is I excite the molecule to the first excited state, and I have a force, because usually it displays. This Frank-Condon force is key in describing molecular spectroscopy, then there is nothing new. But now you see, this is a force that will drive the phonon. But if we do it in this way, and we have it in a cavity, there will be the lower and upper polariton for those energy surfaces. And that's what we did. And then we were not expecting anything interesting. Then you get, okay, the transmission is lower polariton, upper polariton, lower, upper as a function of the number of molecules. But then you get to this point, which is, I forgot, it's around a few tenths of molecules. And instead of reducing the lower polariton, you get an enhancement. Okay? And then basically it means that you have transfer of energy between the polaritons, and which will couple to the phonon. And this is really interesting because it happened when the Rabi splitting, and this is the key, is equal to the vibrational frequency of the molecule in the ground state. Then you are exciting, you create a Rabi splitting, and this oscillation of the Rabi splitting is an additional nonlinear field that drives the Raman mode in your molecule. And this is really interesting because now you can take the idea and do it for benzene, which is the breathing mode, and I show you what is happening when you get to the transition and it's the Rabi as a function of the frequency. All of a sudden, the displacement of the mode gets enhanced by a factor of 6. Then it's a way to enhance the strength of the force acting on the molecule. And this is really nice because it's nonlinear phononics in action in which you use only the Rabi splitting. And this is independent of how strong the light matter coupling is. It's just the fact that it's a resonant process. Okay, then I give you ingredients about how the force could be big, how we are using this collectivity to transmit that into locality, and now comes the hypothesis that I want to run through you, because this is a generic effect, works everywhere. Sorry, I did it here, as I wanted to disclaim, with electronic excitations. You could as well do an IR excitation of a phonon that is coupled to an acoustic phonon at lower frequency. The only thing you need to have is that the splitting of the IR mode is such that couples to another phonon and works in all type of cases. And this is really efficient due to the cavity field. Okay, and then I'm done. I want to tell you what we think is the idea, because this doesn't solve the problem. And then I want to say this is electron-electron interaction and electron phonon that you all know how to solve. Then there are many techniques that has been discussed during the conference to solve. But there is something which is more important in our field, is how is the intermolecular interaction, no? Which is van der Waals and beyond. And thus, if you write it, looks like a sort of dipole-dipole interaction. This is something that, Roberto, you have worked on this electrostatic. It's very much the same. In fact, it is the same in nature. The only thing is that these long-range intermolecular correlations, the beauty is that now you can really cast it into a term that looks like a matrix element with two type of dipole model, Pi, Pj. And this is the spin glass model. Okay? And then what we did just recently is we proved that that is a spin glass with this correlation function. Then you can get it with the separation. But the most important thing is, and this is what is key, the sign of the interaction you can prove is negative. This is really important because if it was positive, there is nothing interesting. And the positive is what happens if you are in gas phase and the system is isotropic. And that's that reason you don't see this effect in gas phase. However, when you go to the cavity and you break the symmetry of the molecular system, you introduce this negative coupling, which is the Parisi model for spin glasses, or the Cherenkov-Kilpatrick model. And now this introduces what I told you. That model has local instabilities that give you the fluctuations as large as you wish, and those are the ones that coupled to the forces will drive the chemical reaction. Okay? That's our proposal, and now it needs to be proven, because I told you that there is a model. We don't know if this works. In principle, it has all the ingredients to work, in which you do the cavity molecular dynamics coupled to the spin glass solution. This is a non-trivial problem by itself. Then I'm not telling you that you solve. And then you have to have both thermodynamics, electron correlations, nuclear correlations, and in this case, we hope that you will be in this regime of the spin glass solution that give you non-canonical dynamics and stochastic resonance. If that's the case, it's a big if, then we will explain polaritonic chemistry. If that's not the case, you have to come up with another theory that we don't know. And that's where we got the ERC synergy approved for the next 6 years to demonstrate this is true or not. Okay, with that I wanted to finish, but before that is this short summary that I hope I convinced you that there is a lot of room in this field of light cavity materials engineering, that we have a theory to do it. And then to just conclude, I wanted to take something that probably Ario knows from Hardy, mathematician in Cambridge, that is this one of the first duties of a professor, to exaggerate what is the contribution to this field. This is probably what I'm doing, but if you take clearly the case of Michele, he's not. He's for granted that it is universally fully recognized that he's not needs to be exaggerated what are the contributions. With that, thank you for your attention and happy birthday, Michele.
Thank you very much. Thanks very much, Angel. Questions?
Thank you for the fascinating talk. Maybe I have sort of not understood, but not maybe, without the maybe. But how do you treat the non-adiabatic couplings between nuclear motion and electronic motion, and couple both with the additional photon field?
Okay, this is a good question. The nuclear dynamics, the non-adiabatic nuclear dynamics is not properly treated here, but these molecules I have chosen are basically adiabatic in this coupling. Those systems, you don't need those nonlinear couplings. Eventually, for other molecules in which you have these conical intersections and all that, this will be extremely important and is not being treated. We have a technique based on multi-trajectory methods or sampling techniques to include those nuclear dynamics. But this was to make more complicated the description now, but it's something that we need to do. In fact, if the systems I show you are of no practical interest, benzene and nitrogen 2, but I chose them just to prevent that problem. The ones that are interesting, we will have non-adiabatic couplings.
Great. Maybe another quick question. So, as a curiosity, very often in this field of cavity physics, cavity chemistry, not many words are spent to talk about what is the cavity in terms of the material itself, and what is at the end, the interaction between what you put inside the cavity with the cavity as a material, as a physical device. So can you comment a little bit on
that's
that?
I show you this simulation of a real mirrors with the electric field. This is the simulation of a real cavity. In experiments, what they take is gold-based Fabry-Perot cavities in chemistry. And they are really not high Q factor, because you need to have a way to get in and out. Otherwise, you cannot do the experiments. And basically what they are is they are cavities which the length is resonant to one of the vibrations, IR vibrations of the molecule. That's the general setup. Once you have that, in many reactions there is no effect, and it's only those ones that has this collective local coupling, that's what we believe, that you do see an effect. And don't forget, always there is a Raman mode somewhere, because you need to couple to the fluctuations, which is E squared. And then the IR mode is coupled due to many molecules interaction, because it's one oscillation of one molecule couples to the other one, but the cavity couples to the E squared. Okay, that's the situation. This is for molecules. For solids, what they do is what is called half cavities. Half cavities, which is, you just keep an open cavity, which is ill-defined concept, but is a surface that acts as a metamaterial and couples to the superconductor.
More questions? Comments? Just a quick question, Angel. Why qualitatively is the electromagnetic field reducing the strength of a hydrogen bond? It is modified and it gets less attractive. Could it be not more attractive?
It could be more. It is. It could be more attractive.
I see. Yes. So it depends on parameters.
It depends on the polarization and on the light matter coupling. And you can do both ways.
I see. So in principle, there's a way of tuning that.
Tuning that. Yes.
Yeah. Roberto.
Of course.
In the beautiful lectures that David Chandler gave in one of these summer school or organized by Giovanni Ciccotti, he was lecturing on electron transfer in solution, and the concept was that this is governed by fluctuation of the polarized medium. And so I think that in this kind of experimental setup with the electric field in the cavity, one could control this fluctuation of the polarized medium and therefore accelerate or do something on this reaction.
I completely agree. I mean, that doesn't need to be really fully quantum. It's those fluctuations of the electromagnetic field are the driving. Yes, I agree.
We have no more questions. Then we thank Angel again. Thank you very much.
Thank you.
Ribello. Talk about Plumed. And by the way, the schedule that I have up here is now shifted by half an hour forward. Okay?
I do that? Does that? Maybe. We'll see. Okay. Excellent. So, firstly, thank you to the organizers for having me here for this trip, for this lovely conference, which has been very interesting, and it's been lovely to catch up with people I haven't seen for quite a long time. And happy birthday, Michele. Unfortunately, I couldn't, for some reason, I seem to have lost all the photos that I have of my time in Lugano. So I don't have anything in my slides, but I thought I'd start with a little story about how I got my job over in Switzerland. So I was finishing a PhD in London and looking for a position. Michele came and gave a talk, which was great, really interesting. And afterwards, I sent him an email saying, can I have a job, please? And he said, I don't have any funding at the moment, but maybe you can find some funding. So I went off and did a half-hearted look for funding online and sent him another email saying, I'm looking, but I can't find anything. To which he replied, I've had some surprising and unexpected. I've never found out exactly what, just those adjectives. I said, can you come up to Oxford to visit me? So I went to Oxford, where I'd done my degree, for my meeting with Michele. And as I was walking into the room, Professor Manolopoulos, who had taught me as an undergraduate, was walking out backwards and bowing as if he was a privy councillor who just had an audience with the Queen. So I went in. The first question I was asked was to explain why I was English and had an Italian surname. And I must have answered that question okay, because at the end of the meeting he said, okay, get in touch with my secretary, Daniela Wirtz, to get your travel reimbursed up here today and to organize your work visa. Yeah, I don't think he ever really knew how little I knew going into that. And although he's very curious about many things, what I do not know never seemed to be one of them. We would go to meetings and people would ask, do you know about X? And I would say no, and Michele would reply, of course he knows about that. So, I'm going to talk a little bit about Plumed.
It's like your mom, she knows better.
Yeah, exactly. So I'm going to talk a little bit about Plumed today, and I'm going to start my talk with a quite provocative statement, given that I was asked to give a talk about the Plumed community. So my provocative statement is... Oh, that doesn't work. Why is that not working? I'll get rid of that. There we are. There is no such thing as the Plumed community. And what I hope is that we'll all still be friends at the end of this talk, and either you will understand what I'm trying to get at, or you'll just think that I'm a pedant. Okay, so I hopefully don't have to explain this, so I can go very quickly through this next part. So what is Plumed? So Plumed is this plugin for molecular dynamics, and it's designed so you have your molecular dynamics code, which works by calculating forces and then integrating the equations of motion. And Plumed sits alongside, and after the force calculation, you pass across the atomic positions. Plumed can then do various things, and Plumed can then pass back some forces, and those forces can be incorporated into the integration. So it sits as this kind of plug-in structure. That's what we call it. People who are less nice than us call it a virus. And the idea how this came about was we wanted something interoperable that would work with many different MD codes, and we really wanted to get away from this idea that the community consisted of a set of users and of methods and developers, and acknowledge how the community actually is, which is this kind of gradient. So there isn't this sharp distinction between people who develop methods and people who use them. To do science, you need to develop methods. That's part of it. And hopefully Plumed facilitates that. So the question is, how do we serve the folks in the middle of this diagram? So this is what a typical Plumed input looks like. Basically, it's like a small programming language. Here, you've got this command at the top that calculates the distance between a pair of atoms. It outputs a quantity which is then called D in the remainder of this script, and you can see we're applying a restraint on this D. So we can think of this in some ways a bit like a neural network, but in which you have to parameterize everything in the code. And the way that Plumed operates is you have a feed-forward network where you basically calculate each of these quantities and pass them around. And incidentally, if you want to make these diagrams, they're made with Plumed. You just do this Plumed show graph and then your input file. And then the second step is that there's a backwards propagation step where we use the chain rule to calculate any forces on atoms. Okay? And this is quite useful. It means that you can do a lot of things directly from the input file by basically combining what the lines of this input and what we call these actions. So for example, here's a slightly more complicated input. Well, it's not really. So here now, instead of calculating the distance between the two atoms, we're calculating the vector connecting those two atoms by adding this components flag. Let's suppose that we want to calculate the director of that vector instead. We would do something like this. So we first calculate the length of the vector in the usual way, then we divide each of the components of the vector by its length, and lo and behold, we have the director. And if you want that diagrammatically, that's how data is being passed through that input. So what we've added, so up until recently, you've only been able to pass scalar quantities between these actions in Plumed. What we've added recently is the ability to pass vectors, matrices, and grids as well. So this means you can, but just by adding that you want to calculate more distances there, you can do the same thing, and notice that the arrows in this diagram are blue now rather than black, and this indicates the fact that we're passing vectors now instead of scalars. So this quantity output here, we now have 3 vectors, one which contains the x components of all our distances, one that contains the y's, and one that contains the z's, and functions work in the normal way that functions work on vectors and so on and so forth. So why is this useful? Well, let's suppose that we wanted to look at a phenomenon like this, where you've got an ordered phase and a disordered phase, so you've got these molecules that line up. We might want to calculate the directors of these vectors, because if we were to add together all of those directors for the ordered phase, we would have something that is basically large for the solid and something that is small for the liquid. And you can do that directly when Plumed without having to write any C++ down. And you get this hopefully reasonably transparent input for calculating that quantity. And you can make this diagram, and what you can see is this mean command here converts these vectors into scalars. So we're calculating the length of the average of all the directors. And another reason we think this is useful is we think we're sort of set up quite well for this transition that we're going to see, that Michele talked about in his talk yesterday, from thinking about things in terms of individual events and moving to the discussion of distributions. Because if you think about a lot of what we're doing within these MD simulations, a lot of the time we're calculating averages. There are 3 ways that we can do averages. We can do a time average, and that's how you implement a time average in Plumed. You can do an average over indistinguishable objects, and that you can do directly in the Plumed input file. And we can do averages over replicas. So we have commands that allow you to gather the data from multiple replicas and write these scripts to do these things without having to implement too much in Plumed. And if anyone is interested in using this functionality, please do just email me, and we can talk about how to get started on those sorts of things. So, Plumed is not just what we develop. It is very much designed as a community code. And we realized it was a community code because we released this Plumed core in about 2014, and then people started asking us if they could add their little bits of software into this Plumed thing, and we said yes. And so we had these modules on top of this Plumed core that people had contributed. These are the original 6. We sort of formalized this process, and now we have all of these various modules inside this thing. This has proved to be an extremely popular mechanism for distributing ideas to the broader community, distributing methodology through this thing. I'm showing you the manual there, and you can see that everything now in the manual, we clearly illustrate who has contributed the particular modules that we're talking about. So we also looked at how how Plumed was being used. This is a map from a number of years ago. Max showed the updated map, which is much more widely. This was done in about 2019, I think. And we realized a lot of people were using this and that there was a real community, and we wanted to sort of promote scientific reproducibility and good practice amongst this community. So we formed this thing called the Plumed Consortium. Incidentally, everyone asks me, like, who's who in this picture, because there are 4 pigeons there, and four core developers. I don't know exactly, but I know that this one is Max. In my imagination, Max is always wearing a blue and white t-shirt. I don't know why. I've never seen him in one. But if I think back to the Lugano days, he always seemed to be in a blue and white t-shirt. Anyway, so the Plumed Consortium, we formed that. And the first thing we did with that was we created this thing called the Plume Nest. So this was a repository of all the data required to reduce the calculations in your paper. So the idea was you would write your paper, you would take your Plumed inputs, bundle them together in a GitHub repository, and then you contribute it here. So you just fill in this quite simple form. And then from that, we have an automated script that basically adds your inputs in here, and you have these examples, and you end up with a page that looks like this. People can view all of the inputs that you used in your calculations, and we run regularly tests to check that it's still working with the stable version of Plumed and the current master version of Plumed, and we give you a badge there, and you can copy and paste this thing, these entries to your website, your own personal website, and they're there for the community to basically get some sense of how to use this code. Recently, for the Feldschrift, we extended this because we'd done a number of tutorials over the year, so we put our tutorials online. We created another similar website for this one, but this one really focused on sort of teaching people how to use these methods. Again, you have a contribute button and you fill in a form. You create a GitHub repository with your stuff in so you can edit it. And if you edit your GitHub repository, this is updated automatically. If you click on Browse, you see all of the tutorials there. I think there's something like, there's 50-odd tutorials now on this site. If we go into one in particular, so we go into Max's on Plume syntax and analysis, you see that you have an introduction page that looks like this, which has a graph on which shows people how to work through the various resources. You can include videos. So these are videos that Max made to introduce this material. You then you can link to the other tutorials, so you can say this one is a prerequisite. If you do this one on metadynamics before you do this one in OPES, it might help you understand OPES a little better, for example. And then you have automatically generated. It finds all of the actions that are used inside your lesson, and there's a click here, and it will open up a version of the manual that just has the actions that are being used and introduced in the particular lesson that you're teaching. And then finally, the instructions look something like this, and you can see every input in these instructions, again, has this. We test it regularly, and we show people that, yes, this is indeed working, and it should work with the current version of Plumed. So I think this is an incredibly useful resource. I'm going to be using this for teaching my StatMech course next year. So thank you very much to everyone who contributed here for basically doing my job for me. And giving undergraduate students a much richer introduction to this subject than I would be able to give them on my own. So that's the paper that we published in the Feldstrom. We put everyone's name on there who'd contributed a tutorial at the time that we wrote the paper here. So the last thing I wanted to show you is that we've updated the manual as well. So the manual that we had when we wrote this back in 2014 had frames. It was very ugly. We've now got this nice contemporary and much more contemporary website that's much simplified. Basically, if you look, you have this very simple menu. This Getting Started takes you to the first Plumed tutorials. The Tutorials tab takes you to the Tutorials page. The Examples page takes you to the Nest. If you click on the modules, it shows you all the modules that are available in Plumed, who wrote them, and there's a landing page for each modules. And if you click on the Actions button, it takes you to a page that shows you all the various actions. It's searchable, and you can basically create tags to group together actions that do similar things. So I'm just going to show you the documentation page for one particular action, alpha RMSD. So if I just go off here and go, so this is what the documentation for a particular action looks like. So you see at the top, we have a badge, 2 badges, one for the tutorials. So this tells me that there are 3 tutorials that talk about this action, and there are, I can't read that number, 15 examples where this action has been used within the Plumed nest. And if you click on those, it opens those pages and it shows you all the examples in the nest and all the examples in the tutorials. So you don't have to do duplication of effort. Automatically, everything is put in one place. You then have a sort of paragraph of text that explains it. You have these examples, and again, want these badges that tell you if the input still, that Plumed is able to pass the input. Inside these inputs, we use fancy features of HTML. So every time you have a keyword, if you hover over it, it opens a tooltip that explains what that particular keyword does in the input. Here you see that I've got an input file here. It's just a PDB. If I hover over that, you can, if I hover over that, you can click there, and you can see what that auxiliary input file looks like in a pop-up. And then also, with some of these actions, they're implemented as shortcuts, so they basically just create a more complicated Plumed input file. So if you look at this action here, you see that this is an example of a shortcut. If I click on this, if I go on, sorry, I've got to have the reactions of pretty quick reactions. If I click on the shortcut there, it shows you basically how Plumed, the various steps and the more complicated input that is being used for that particular action. So people can get more of an insight of what is being calculated when you're using these more complicated methodologies that do, and they can see how some of these CVs are constructed. So, having messed up my slide there. So, I said at the start that this is not that this was in the community, so what do I think this is? Well, I think that Plumed is a service. It's something that has been constructed by the community to serve the community. And services, when services grow, they don't turn into communities. What they turn into is monopolies. And if you want to be convinced of that, you only need to look at the history of the last 20 years. If you think of any of these companies, these are monopolies. And monopolies are bad. And really, Plumed, the reason I don't like the phrase the Plumed community is it puts a primacy on Plumed, which is not the main thing. The main thing is the underlying community that develops this thing. And this is no longer serving the community, then it's time to replace it. So I wanted to finish by talking about some things that maybe could be investigated by, and that would be bad if Plumed became a monopoly in this area. So if we think about Plumed was developed, the first version of Plumed was developed in 2009. The second version, Plumed 2, was released in 2014. Since 2014, we've had the release of TensorFlow, PyTorch, JAX, and this field is evolving incredibly rapidly, And if we were to develop Plumed starting now, it's not clear that we would develop it in the same way that we would have done in 2014. So if this is all to say, there is value in revisiting some of this stuff again and doing these things in a different way. Please do it in collaboration with us if you can, but if you don't want to, if you want to, but if you don't want to, that's also fine. And then the second thing, as I said, it's not about there are developers and there are users, there is a core of people. The second thing concerns this stuff of the nest and this reproducibility crisis that people talk about. So firstly, I don't like the phrase reproducibility crisis. I think what we have is not a crisis. In 1985, we didn't say that there was an accuracy crisis in response to Carl Parinello. I think we just have some new tools that can be explored. And there are many different ways of exploring those tools. And it would be a disaster, I think, if we ended up in a situation where we produced one universal tool for sharing scientific data, some company privatized that tool, and we would end up with the same economics as we have with journal articles, where we pay to basically release simulation data and we pay to access it. It's really important that we keep it in the community in order to develop these things in-house, keep them small, so that they don't get exploited by these private companies that are not necessarily in our best interest, doing things that are in the best interest of science. And that's the point I wanted to finish on. So I came here a while ago and I gave a talk and I was told that the ending was a bit depressing. And I've got a kind of depressing ending for this one. So there's this book which I read recently by Mark Fisher, called Capitalist Realism, where it talks about the state of the world and how there are these invisible barriers that constrain thought and action and what it is that we can do. And how it is that we can approach the world. And if you think about the political situation in the world at the moment and what is going on, it's pretty horrendous, and it can sometimes feel like you as one person cannot really do anything to make a difference. But I think the most important thing that I learned during my time working for Michele in Switzerland is that there is a freedom in not thinking in terms of these barriers. Freedom is about working in a way where you hope that the world adapts to the way that you want it to be, rather than the way that it actually is. And for that lesson, I'm enormously grateful. So thank you, Michele, and thank you all for your attention.
Thank you very much, Gareth, for the talk and for the message. Mm-hmm. Thank you.
Thank you, Gareth. And I'm standing up to express the gratitude, mine and our community, for the jolly good work that you're doing. And I think Plumed has been instrumental in making metadynamics and OPES so popular in the community. And so I think we should give a big round of applause to Thank you again.
Questions?
I won't comment on capitalism, but I want to comment on on the reproducibility crisis or perceived reproducibility crisis. I think we are in I don't have so much experience as some in this room, but in 25 years of doing this kind of job, we have never been in the position of being so reproducible as we are now. So now we are uploading all our inputs and outputs to some extent. It's becoming common practice in my group and in many groups. So I want to end on a very optimistic note on that side, and also with tools like Plumed and so on. We are in a reproducibility era, not in a reproducibility crisis, at least for what concerns simulations.
Yeah, no, I would agree with you that we're doing much better on this, but it's just I don't think there ever was a crisis. That's my point.
More questions? Comments? Not? Then we thank Garrett again. Half an hour. So it may be we reconvene at 11:30. 11:30.
It's not connecting. Well, no, that's what I'm trying. It's not.
You can try directly this one. Did you try already?
Well, yeah.
Usually it should be better than the adapters.
Skip one step.
Well, maybe.
Yes.
Did you try the DVI? It worked great on mine. Yours is the same machine. So.
Something is happening. Something's happening.
Something is happening.
Okay.
I don't know.
Now just try.
Presentation mode.
Presentation mode.
Very good.
Okay.
The problem is that is inverted.
Yeah.
Presentation is here and here is. I think yes, you have to screen.
We got it.
Solo che l'unica cosa che manca è il numero. Noi io ti aspetto a quel punto e andiamo insieme, no?
Sì, io finisco e
Io solo mi metto dietro.
faccio questa cosa brutta di uscire subito.
Sei già organizzato?
Solo il pointer, uso uno dei miei pointer o ce n'è uno?
Credo che c'è uno qua che è qui dentro. Io sono, diciamo, sarà un secolo che non lavoro qua, ma penso che questo oggetto qua
Dovrebbe pointerare.
dovrebbe pointerare. Sì, è molto, ma con questa storia lo hanno ridotto apposta per le leggi.
Sì. Sai che in aeroporto a Ginevra
L'hanno sequestrato.
me lo volevano sequestrare, mi hanno detto ma dopo se lo sequestriamo ti dobbiamo portare alla polizia, devi pagare la multa, rimani lì delle ore.
Tu ce l'hai, tiralo fuori, no?
Io ce l'ho, quello verde vecchissimo, avrà 20 anni.
Esatto, rispettabile.
Non hanno visto che gli altri organizzatori sono c'è mai hanno pensato il volo che mi sta vincendo ormai subito succede una cosa
Non leggeva, ma non credo che sia importante. Purtroppo queste cose le stazionali.
no, ma che starei per qua.
Sì.
Ok, quello è qua.
Answer is I don't know, I don't believe it.
Vediamo se questo funziona. Poi io ho una presentazione lunghissima, ho 150 slide, perché lo slide è quindi quando mancano 5 minuti
Ti faccio.
sì, perché poi vorrei andare alle conclusioni che sono la parte più importante,
Certo,
dove ci
certo.
sono le varie challenges del
certo.
campo, del settore. Quindi
Sì.
è uno slide deck, vedi, sono 152, ma perché continui a mettere diapositive, non sai mai quali rimuovere e dopo quando lo prepari,
guarda,
alcune le cancelli.
Ti confesso che ho lo stesso problema.
Dopo, man mano le metti hidden, però poi rimangono lì, dopo non sai mai quali togliere.
Sì, ma poi non è da sequestro, questa è una cosa, anche questa moderatissima. Io pensavo uno di quelli che
no, però, cioè
tipo Star
vecchissimo
Wars.
e mi hanno guardato qui e hanno detto, non so dove l'abbiano, classe 2. Hanno visto lì che era classe 2 in aeroporto e mi hanno detto classe 2 sono vietati, le dobbiamo sequestrare il pointer e bla bla bla, eccetera, eccetera.
Questa è una di quelle cose che in una cosa italiana non succederebbe mai.
No,
perché non
no,
saprebbero
no. E poi dopo mi hanno detto si ritenga fortunato perché a Ginevra non a Zurigo, perché a Zurigo
Ti
sono
facevano il culo così, esatto.
già a Ginevra sono un po' più
Esatto, sono un po' più francofoni.
vabbè, la lascio già in presentazione, no? Così.
Sì.
Tanto
Good. So we are ready to start for the very last piece of our session and of our conference, and that will be with Andrea Cavalli, who speaks about totally fully dynamical docking. Andrea. This way.
Okay. Good morning, everyone. Thank you very much, Ali, for the invitation. Happy birthday, Michele. And today I will talk you about our attempt to transform a process of very well established in pharmaceutical industry, which is docking, in something based on molecular dynamics. And I will mention the historical interaction with the group of Michele, who opened the way to the use of metadynamics and more in general and unsampling methods, which are the technological and physical core of what I'm going to show you today. For this, let me tell you where I'm now. I'm in Lausanne at EPFL. I have the honor to be the director of SICAM, which is a pretty historical and well-established international organization for promoting computational science to foster societal progress. SICAM was established in 1969. It remained an organization pretty small for many, many years, then started to grow, mainly in Europe, and then in 2019, the SICAM Council, which is the second major governing body, decided to open also to non-European organizations. First one in 2019 was the National Academy of Science in Beijing. Then, a couple of years ago, the University of Chicago. Then, the Academia Sinica in Taipei, Taiwan. And finally, last April, we approved the new membership from the University of California at Berkeley. We have several activities. Mainly, SICAM is a bottom-up association organization. Still, we do something also top-down. In particular, recently we signed last year a memorandum of understanding with ICTP, mainly dedicated to computing in Africa. We ask to European supercomputing centers. For the time being, 2 of them agree to do this, CSCS in Lugano and CINEC in Bologna. We are discussing with ULIC and also with others in Europe to have computer time for free for African groups in computational sciences. The call is open since a few days, so please apply or ask to your collaborators in African institutions to apply, because there is a pretty good amount of computer time for running simulations in those countries. Now, science. This is the outline of my presentation, and the outline of my presentation is, will finish probably, I don't know, because it's pretty long, so I ask the chairman to tell me when 5 minutes remain. Because computational methods in drug discovery should be able to provide prospective ideas. We need new ideas to be predictive and to be accurate. I don't know whether Ali is still around, because based on what he said yesterday, this is the end of my talk. And it's complex. It's complex because we are trying to apply physical methods that our community, I'm a chemist by training, that your and my community has developed over the years for targeting complex problems in chemistry, biology, and pharmacology. Pharmacology is the link between chemistry and biology, which is even more complex. And drug discovery is pharmacology, is mainly pharmacology. So even though it's true that many startup companies are failing because they are unable to be prospective, predictive, and accurate, I would like to show our trajectory, the trajectory of my groups over the years in Italy and now in Switzerland, to try to address this problem.
The goal has not been reached. So the most important slide of my presentation is the last one with the open challenges, because the message, the good message for the younger ones is that there is still a lot of work to do, at least in this field that I know pretty well. So this is the fil rouge. Docking is something that statically or semi-flexibly study how a ligand binds into the receptor, into the binding pocket, and we wanted to transform in something completely dynamical. Why? I don't need to explain you why, because proteins are flexible, molecules are flexible, everything happens at 300 Kelvin or 310 in our body. So, just a quick recall to what docking is a process made by two steps, which are intuitively very simple. We need to put the drug into the binding pocket of the target, and then we must estimate the affinity of this new chemical entity for the biological target. And also this slide is very trivial. Why MD? Because if we are able to run pretty long, super long and extensive MD simulation, if the free energy or the potential energy surface is very simple, then we can estimate the free energy difference, and the free energy difference is the affinity. And the affinity is important, even though not sufficient, because many times also the kinetics, particularly for the next generation drugs, is very, very important as well. And kinetics is even more difficult because you need to get information about this point of the free energy surface. When and where I started this trajectory? One medicinal chemist, pretty famous medicinal chemist, came to my desk. I was a PhD student, asking me, I synthesized this molecule, the light blue, which is very potent, which is an interesting drug candidate. I would like to know how it binds, because we would like to make some chemical modification. Can you run this fancy docking or whatever? So I tried with docking, and was basically impossible to dock reasonably this molecule because it's super flexible. It's a diamine-diamide. So it's not only complex because it's flexible, it's also complex because we have two titrable groups plus different automeric forms. So I'm starting to bring you to the final challenges: protonation, tautomerism. So I try with MD. I install Amber. Don't remember whether it was Amber 3 or Amber 2 or something like that. Full of problems to run simulation with united atoms force field. Not all atoms because it was too expensive. I dock the molecule, I build the molecule manually into the binding pocket, and then I run few nanoseconds, probably 1 nanosecond or even less, of MD simulation. And finally, the binding mode was rather reasonable compared to the crystal structure, which came after. And then during the conference, I was invited as a student around the 2000 year. I said, I have a scientific dream to study. This is an animated GIF done in 2000. I have a dream to, I want to show you again. I have a dream to study fully dynamically this process, and I think in a few years this will be possible. This is taurosporin, an anti-cancer drug binding to CDK2, cyclin-dependent kinase. Pretty easy molecular complex, also because taurosporin is very static and has no flexibility. And then the very important interaction with Michele's group. Francesco, Gervasio, Davide Branduardi. This was the small team working together to address the problem of computational drug discovery dynamically. So metadynamic was invented a few years before, even though publication is 2005. We started to work on this project soon after metadynamics was released. And we published together 4 or 5 different papers addressing different challenges in computational drug discovery. And also large-scale conformational motions with Anna Berteotti, and also rescoring for docking, for conventional docking, using metadynamics for rescoring. It was pretty interesting. And the scientific dream started to become a kind of reality, even though it was still not really possible to study big molecules binding spontaneously. We were on an interesting trajectory. We also applied other enhanced sampling. Here, for example, we use STIR-MD, which was appearing in the literature as a potential tool for biology in general, but never applied to drug discovery. And here we apply to drug discovery in a prospective way, not accurate, but at least prospective, because we design the molecule, the blue molecule, we predict, we synthesize, and the molecule was potent. This is a binary message, potent or weak, no quantitative, okay? Then I had a group of, a multidisciplinary group of experimentalists, so many of the computational ideas I could test experimentally with my colleagues working in the field of pancreatic cancer drug discovery, and we developed molecules using these approaches, but this is another story in collaboration with pharmacologists and oncologists. And then the advent of GPU, and the scientific idea became reality, because we could start running multi-microsecond long simulation. The simulation was done more than 10 years ago, without any constraint, without any enhanced sampling, simply brute force MD. When I was presenting this paper at conferences, the first question was, what you learn? This is brute force MD. You have computer power, you run simulation. It's far from trivial, because we were moving from nanosecond simulation to multi-microsecond simulation. So even trivially, the numerical stability for super long simulation was not tested. These kind of studies were done at least by 2 other groups worldwide, Gianni in Barcelona and David Shaw in New York. And it was possible to study dynamically the binding of a ligand into the protein. And the final structure was very similar to the crystal structure, with a root mean square deviation, a geometrical root mean square deviation, less than 1 angstrom for the heavy atoms. To analyze this data, we apply machine learning. Very few people were speaking about machine learning 10 years ago, but we use as a tool to analyze the terabyte of trajectory data, simply, nothing more fancy than this. Then we started discussions with pharmaceutical companies, and they said, look, very interesting what you are showing, but we have no time to wait 6 months for one single molecule to bind into the biological target. So together with Walter Rocchia, we designed a collective variable for drugs, which is inspired by nature, which was inspired by nature, because it's a simple electrostatic variable spread over the atoms of the ligand and spread over the atoms of the binding site. And by enhancing the sampling of this fictitious electrostatic attraction, we could reduce simulation time from the multi-microsecond time scale to the nanosecond time scale. So the dynamical docking, the dream of 2000, was possible in a reasonable amount of simulation time. This is an historical benchmark example for docking, because it's donepezil, which is an anti-Alzheimer drug, binding into its biological target, and there is no one single docking tool able to reproduce the crystallographic structure because there is a backbone motion during binding. So backbone should open, the backbone of the protein should open, and if you need to open the backbone, you need to study the protein dynamically during binding. This was also possible with membrane proteins, so to show the general applicability of the methodology, and here also to show how the electrostatic bias was tuned over the simulation, automatically over the simulation. While the ligand was binding, the electrostatic bias was getting closer and closer to zero to leave the system then to spontaneously evolve into the binding pocket at a certain point. Then was applied to a series of compounds and was published here, if you wish. Then, sending these papers, every time referees were saying, yes, look, anyway, collective variables are complex. Can you do something? Try to do something which is totally independent of the predefinition of a reaction coordinate, even though it was electrostatic, so it was rather general. You have a drug, you have a drug, you have a receptor, you spread the electrostatic attraction on the heavy atoms of the drug, on the heavy atoms of the binding pocket, so it was rather general. But we wanted to develop something which was completely independent on a predefinition of a reaction coordinate, which is not completely true, but was accepted in this way, because anyway we needed to establish a geometrical, at least a geometrical constraint along the direction of binding, and then we enhanced the sampling of the drug into the binding pocket, and as you may see, he is unable to escape the cylindrical constraint, but again, finally was able to get to the final binding pose. So here are some numbers. The RMSD was good also in this case. The method that we released to the community, and the paper which we entitled Reaction Coordinate Independent, even though, as I said, there was a pretty strong geometrical constraint. But this is the end of step number 1 of docking, posing. So posing is doable? Yes. Now, I wait the end of the talk, but I guess that many of you are thinking, I can use AlphaFold 3, I can use both 2. Yes, but then I have the answer for you, so ask this question if you want. Just to say that we are wasting time, because anyway our simulations can take 3-4 days. AlphaFold 3 takes 1 hour. Both 2 even less. We tried last week, and in 30 minutes you can create super reasonable complexes, drug target complexes. Still, I think that the molecular dynamics and enhanced sampling can say something, even though AlphaFold 3 and both 2 are spectacular tools. No question about that, spectacular tools. That they got the Nobel Prize, they are spectacular tools. But, there is a big but. Then, posing is doable, yes. Scoring, I anticipate, no. And now Ali is fully true, or the article in the Financial Times. And so, why no? I will tell you in the end. Because there are many, many, many open challenges that the community should address. Not in an incremental way, but a real breakthrough for computational drug discovery. Then, just an educational slide, how to calculate free energy in drug discovery via chemical transformations, where you simulate the change of interaction potential between the water and the binding pocket, free energy perturbation, thermodynamic integration, or double decoupling, and implementation by Benoit Roux of one of the 2 approaches, or path-based methods, where you want to learn about the binding path, the binding trajectory. My group tried to work more in this direction, even though we also developed something here. But thanks to the collaboration with Michele, our idea was to get also information mechanistic information, which are very, very important. And the collective variable more interesting for drug design was the one developed by Branduardi, Gervasio, and Michele in 2007, the path-based collective variable. So we started from this, then we developed a new version of this collective variable fully suitable for drug discovery that I will tell you now. I think that 90% of the people in the audience know much better than me what this collective variable does. And then we develop our protocol or method, if you want, where we define a new approach for the definition of the collective variable using a principal path in data space. So we generate a data space, a preliminary, a very quick data space using adiabatic bias molecular dynamics simulation method invented by Pietro Ballone in 1999, coupled with our electrostatic collective variables, which in this case was an unbinding collective variables, not a binding. So in the example that I showed you before, the electrostatic attraction should be maximized. In this case, the electrostatic attraction should be minimized, should be brought to zero between the pool of atoms predefined. In this way, running several different multi-nanosecond adiabatic bias MD simulation with the electrostatic collective variables, we generate a data space. And in this data space, we generate a string corresponding to S. And we applied metadynamics. We identify the free energy, the Landau free energy. We split the potential of the plot of the Landau free energy in the two regions, bound and unbound, and we integrate and we calculate via partition function the free energy using the simple equations I showed you at the very beginning. Then problem number one, where we cut the trajectory for identifying the bound state and the unbound state. If we have a very, very simple free energy surface, then it's rather trivial. You cut here. Left is bound, right is unbound. But if you have a more complex profile, where do you cut? And we use, again, a method coming from clustering, in this case, the Elbon criterion in clustering. And when there is a jump between the two distributions, we cut and we said, on the right is bound and on the left is unbound. And then we apply this method in a prospective way. As I told you, I was lucky enough to have an experimental group working with me. And so we design new GSK 3-bit inhibitors. We tested them. We evaluate the binding free energy. And then we synthesized and tested via SPR, via surface plasma resonance. And the objective for drug discovery, if you want to convince medicinal chemists to synthesize your molecules, you have to be predictive with an error no more than 1 kilocal per mole, otherwise they synthesize molecules. So if you want to convince them not to synthesize 200 molecules, but only the 50 that you are proposing them, you should be very, very accurate, otherwise they go independently. This happened to me many, many times. And in this case, we were rather predictive. I don't know how many of you, probably in this case not many, know this target, GSK 3-beta. And so those of you who know this target may say, you like to play easy, because it's a pretty easy target. It's a kinase, super well-known target. The series of molecules are based on a predefined scaffold for which there is the crystal structure available. These are our chemical modifications. Still, the chemical complexity. Look at this molecule. I don't know how many chemists are in the audience. in these molecules, we have many different titrable groups, which is the protonation state of these molecules, which is the tautomeric form of this ring. How this impact on binding, how this impact on the population in water and on the population in the binding pocket, and on the population in the transition state, even more complex. So we tried different protonation states based on the prediction of some heuristic predictor of protonation states, and we tried to balance the partition function based on the different protonation states. You will find in the literature very, very few papers addressing the population of the different protonation states of drug during binding into the biological target. And this is complexity number one. Then I asked, when we finished this paper, to one of my PhD students, can you tell me how many drugs in the market, among the 3,000 drugs in the market, have titrable groups? 70%. How many of them have two titrable groups? 15%. So 85% of drugs in the market now have at least one or two titrable groups. This means that the equilibrium between different protonation states is critical for all the pharmacokinetic steps in drug discovery and development. So we cannot design molecules without titrable groups. I can open a pharmacological parenthesis. Which are those which do not have titrable groups? The general anesthetic, because they bind into the membrane and they modify the membrane plasticity. So they are super lipophilic molecules. 5 minutes, okay. So I must go to the end, as I promised to Ariel. As I told you, this is the historical slide deck, so it's pretty long. Okay. You wanted to know something newer, I guess. These are the most recent evolution in my group, studying RNA-protein interaction, RNA-drug interaction. This is an even more complex problem because RNA can generate many different pockets. And even if you look at this very simple molecule, which is an RNA riboswitch binder, this molecule can have many different tautomeric states. And you get different free energy profile if you use different tautomeric state, which is the one we run couple cluster simulation. And couple cluster simulation provide a tautomeric state which is totally different from the crystal structure. But we know that in the crystal structure we don't have the hydrogen, so we wrote to the crystallographers and we asked, is it possible that we have this different tautomeric organization? Again, chemical complexity. Then dissipation is another topic that we are addressing. Look, these water molecules, and here we have one of the major representative in developing water molecules, force field, have been developed for equilibrium simulation. When you run an unsampling, you have a lot of dissipation, local work and local dissipation. And look, which is the discrepancy using different water models running an unsampling simulation in the free energy. And then the entropic correction. We recently realized that the entropic correction for the unbound state in many cases was totally underestimated for the entropic penalty. And in 2-3 cases that we simulated, stay tuned because we are publishing this paper or is already on the web, we identify a difference in entropic penalty between the two states of more than 6 kilocal per mole. And this is the last slide of my presentation. So, dynamic docking. Dynamic docking is nice, is my dream, as I told you. And probably posing is possible, even though, as I told you, alpha fold 3, bolts 2 are certainly much, much more faster than our methods. Relative binding free energy is possible. Many pharmaceutical companies are using free energy perturbation for small chemical modifications. But alchemical transformation for absolute binding free energy has major problem of convergence. And path-based methods, these are very much dependent on the definition of the collective variables. Even though the path-based collective variable can be okay, as I showed you, it is very much impacting on the shape of the potential of mean force, which then impact on the partition function definition. And then force field parameters. What about metals? There are many metal-containing drugs, and there are super many metal-containing targets. How do we parameterize metals? Water molecules for enhanced sampling. I showed you in some cases we have an error of 6-7 kilocal per mole using different solvation models. And covalent drugs. I was in a conference a few days ago with a guy from Pfizer saying, in oncology, we are mainly focusing on covalent drugs now. Do we have methodology to run dynamical docking for covalent drugs? And then the two final chemical problems, so chemical challenges, if you wish, linked to the pKa and to the tautomer selection and tautomer equilibrium. Consider that both of them are dynamic and can change over binding, over the trajectory. So keep in mind that all of them may require to be focused very, very deeply to try to address the problem. A possibility? Yes. Could be machine learning potential? Yes. Where we are in biology for machine learning potential? We can run simulation with a time step of 1-2 femtosecond? Yes. How much shorter? How shorter is the integration of the forces using machine learning potential in biology? Is 3 seconds per 1,000 atoms on one single GPU with an exponential growth. And we run simulation of at least 100,000 atoms. So you can understand how much shorter, for the time being, the force calculation using machine learning potential is in biology. These are the people who contributed to this work. And again, thank you, Michele, and happy birthday. And thank you very much for your kind attention.
Thank you very much. Questions? Comments? Better come down.
Thank you.
Comment about the RNA. No, but I want to comment on the ligand RNA. We have done recently some chemical calculations. Seems that the field of the RNA is so large that using the resp charges might be a big limitation.
Yeah.
And so RNA, I think, has this additional problem that it's a polyelectrolyte, and it's going to be very difficult to study with standard force field, I think.
Yeah, I completely agree. And there are a couple of attempts of machine learning potential, but in this case, I would rather go for QMMM calculations to start with. I think that for the time being, one of the major complexity of RNA is due to the intrinsic flexibility, and so I can anticipate my answer to AlphaFold 3 and both 2. Due to the high intrinsic flexibility of RNA, one of the most difficult tasks is to identify the correct pocket where you can address the drug discovery and the drug docking. This is true for also many proteins, which are increasingly more interesting in pharma companies, which are the intrinsically disordered proteins, or, if you wish, intrinsically disordered domains, which are even more widespread within proteins. There are many proteins which are structurally ordered, but then where the drug binds are intrinsically disordered, and these are representing between 20 and 30% of the entire structural genomics. And for those, I guess that AlphaFold 3 or both 2 are still not fully able to identify the binding, the final binding. For them, I guess that enhanced sampling and molecular dynamics in particular, combined with a reasonable force field, can be still the solution, and is the point where we have to focus. And is a pretty large plethora of target. Without speaking about the multi-macromolecular complex species of chromatin or heterodimer or an undecamer. We recently discovered RAD52, which is made by 11 monomer, 3 of them fully flexible, and is an important emerging target for anti-cancer drug discovery in pancreatic cancer. So I think that are tools, we can use them. These are other tools which are complementary, and there is no one single solution to the multi-problems and the multi-complexity of biology and chemistry. This is my impression.
Questions? Not, then we thank Andrea again. Thank you very much. Machine learning approach to dynamic fluctuations. And here is the microphone. You want to use this? Okay. Try if it works. Good.
Does it? Okay, it does. All right. Let's see. We're in business. Thank you very much. I will try to go fast. I know everybody's tired by now. Apologies for the slight change on the title, but I had to change things up so I could travel. We talked, of course, about these problems throughout the week, but today I will show you some of our work that we are also trying to contribute in how we can tackle the configurational diversity and local structure and reactivity. A few things about myself. I came to the United States in '94 for my PhD, which I did in electronic structure at Iowa State with Mark Gordon. And I meandered, through UCSD with Peter Taylor, Caltech with Aaron Cooperman, and eventually I ended up at PNNL. And I have been in the national lab system since then. In 2022, I moved to RNL. And it's the national labs are a special place for research. It is the emphasis is a lot on collaboration between theory and experiment. So whatever we do is always related to experimental work. You're all invited to visit anytime, but I wanted to say that I grew up in Kalamata, which is only a few kilometers away from Messina, the original Messina, that colonized Sicily. So Michele and I have been joking that we're probably related somehow. So I first met Michele, I think it was 2015 or 16 when he visited PNNL. And somehow I was adopted into this community. With my longtime collaborator, Roger, we visited Lugano in 2016, and after that I visited several times, and I have very, very fond memories. What I want to talk about is we're trying to understand what impacts chemical reactivity and how we can handle the complexity. And I will illustrate that with a few examples. The first one is my first collaboration with Michele and how it shows the power of metadynamics. And then I will move on into some recent work and current work we are doing on how we can leverage the global optimization in data science to determine multiple pathways. So when during that first visit, we started talking about, at the time we're doing work on supercritical CO2 from the point of view of sequestration and reactivity. And supercritical CO2 is a very interesting beast. What really impressed me, but also bothered me a little bit in the literature, is that there were all these papers that were looking at how CO2 gets absorbed and becomes reactive. And they would always quote this reaction, which it makes sense when you are in an aqueous environment, but not in the supercritical CO2, because there water has a very, very low solubility. And in fact, in a previous study that we have done, we saw that in general, water is actually dispersed mostly as monomers, right? So how is this all happening? And so we started doing these metadynamic simulations. Only even for this simple system, you still had to choose the right variables, very specially tailored collective variables after Pietrucci, and this work was done with the lovely Daniela and Emanuele Grifoni. So these variables are there not to take into account only the bonding that will occur, but also the local environment. And as you see here in this summary picture, this reaction, in order to take place in the supercritical CO2, the barrier is almost as high, almost over 2 EV, right, like in the gas phase. While, of course, in the water, it becomes a lot easier. And another interesting outcome of these simulations is, okay, here you see this very narrow channel that leads to the trans carbonic acid. In general, the transition states turned out to be fairly similar. However, the one in the supercritical CO2, bye Simona, actually goes straight to the bicarbonate and not into the carbonic acid that then dissociates. So quite different from what, from this blanket statement in the literature. And of course, through the metadynamics, I'm preaching to the choir here, but it makes also quite easy to quantify the enthalpic and entropic contributions. And then we can see that in the case of the supercritical CO2, we have very strong contributions from the entropy, while in water, both enthalpy and entropy contribute quite a bit. All right. So I think several people mentioned, catalysis and the active centers, and how understanding what they are and where they are is essential to catalysis. Of course, catalysis is not about just one reaction, but instead the multiple reactions that can happen at the same time. And of course, we have to have large enough models to be able to represent our catalytic sites correctly. So we struggled with this issue, because even when you start all these large simulations, you really need to start from a very reasonable, very good starting structure. And the bigger your system, the more difficult this becomes. So a few years back, we started looking into a global optimization method that can help us actually go to a very good starting structure. Of course, the problem with a global optimization procedure is that there's no mathematical condition that can guarantee that, so you have to have a heuristic method and then compare the structure and see where you are. There are other people who have thought about it, of course, over the years, and there's many, many methods. One of the issues is that a lot of these codes can be proprietary, and most importantly, cannot really handle the large number of atoms, right? So we wanted to do something more extensive. Today I will briefly speak about, there are different types of methods to do these things. I will focus on the artificial bee colony and the genetic algorithm. So with one of my former postdocs, we created this method. Then it was still at PNL, Northwest Potential Energy Surf Search Engine. And this is based on the ABC algorithm, which stands for Artificial Bee Colony Algorithm. It basically takes, imitates the way the honeybees are finding their food source. And essentially, it is based on 3 different bee types or operators. One is the employed bee, which essentially looks at 3 known structures and applies the trigonometric mutation. And if the structure is good in terms of an energy criterion, then it keeps it into our ensemble. If not, it throws it out. The onlooker bee looks at the most stable structure that we have in our ensemble and then deforms it. Again, we compare it. If it's good, we keep it. If not, we throw it out. And the scout bees create completely new structures. So the fact that we can do these comparisons and actually throw away the bad structures, that means that it is self-adaptive and it keeps increasing the number of good structures into our ensemble. So after that, we decided, so that previous code is C++ based, and we decided to also write a Python-based version that makes it a little bit easier to integrate with data science methods. So this is, we call it range. It has additional functions, and one of them is the integration of a genetic algorithm that helps us actually go to the minimum much faster. In the previous version, we noted that sometimes you can get locked into a local minimum, and no matter how long you run the simulation, you're still staying there. So it was an issue of premature convergence. So now the combination with the genetic algorithm, however, seems to be able to overcome this issue. And we tested it by looking at taking the Miller-Brown surface, which is has an analytical form, and it is used a lot to benchmark things like that. This surface has 1 global known global minimum and 2 local minima. And so we use this to evaluate this performance of the hybrid algorithm. So you see that, so the red point here is actually the global minimum, and all the yellow points are the ones that came out of the global optimization process. So to ensure statistical reliability, we ran these for several tests for 5,000 points. And then the first 100 structures were randomly generated. And you see here, if we were to compare all these different types of algorithms, just the genetic algorithm, you see that it really goes very flat almost. And our previous implementation of the in the NWPS, it goes up fast, but eventually it still gets trapped. And the red line is the new implementation that shows that we can get there more quickly. These are some of the examples. In the first one, you see we started with 6 carbon atoms just in a box, and eventually it found the fullerene structure. In another case, we looked at a functionalized fullerene, and comparing with the literature, we found several new minima. It has been tested on a variety of systems, and with this method, we can do several hundred atoms. Finally, a final example is how it can be used to compute ensemble average properties, like spectroscopic properties, for example, XFs. Over the years with Roger, we have done a lot of studies where we had to calculate, to compute XF spectra, and what we have found out, compared with a standard method, just optimize the structure, take the last configuration, and calculate the spectrum, we found out that if we run an MD and then with sample configurations, then we get a much better agreement, like here showing in the upper plots. So one idea was, okay, can this global optimizer actually help us avoid even the MD that can take quite a bit of time? And sure enough, by taking only 10 or 20 structures, the lowest lying ones, then we can get even a better agreement for XFs. All right, so again, we talked throughout the week, we talked a lot about the parallel reactions that happen in catalysis, and this actually is from an old paper that we did with Roger 2010. And it took us about 2 years to run all the calculations. At some point we thought, okay, is there any way that maybe you can take advantage of this global optimization procedure to determine reaction paths much faster? And so the idea then was to use the global optimization in the basin of reactants and then do the same in the products, and then use neural networks in between to determine transition states. And so we did that using GANs. The GANs usually essentially use the charges on the configuration of the structures. And then the generator creates a synthetic transition state. The discriminator checks against known structures, and then if it's realistic, you keep it. If not, we go through the cycle again. The important thing is that you can allocate transition states in seconds, and even for large systems. And for those who have done NEBs and transition states, even in the gas phase, understand how much better this can be. And so this is one example from our recent work. We are looking in our BES catalysis program. We're looking for a reduction of, say, CO2 over supported nanoparticles. And so we tried that, and we get a barrier of about, about 17 kcals per mole, and our experimental colleagues measured the activation energy, which comes out to about 14, 15. So that is pretty good, I would say. The other thing is for the practitioners of NEBs, if you take that transition state and you include it in your NEB configurations, it can converge it a lot faster than not having it. So finally, the last thing we did was to okay, what happens if I have my reactants, my products, and let's take the lowest 10, 15 structures, whatever it is, that may be, especially at elevated temperatures, that may be relevant to our catalytic processes. So if you do that for 10 reactants and 10 product states, you can potentially have up to 100 reactions, right? Even for this simple system, you can have, not all of them are realistic, but even for this, you can end up with up to 35 or 36 possible reactions, and it looks like that. But having this picture, we can actually create a graph representation of what reactant and product connects to what, and that makes a lot easier our life when we want to build a kinetic network and kinetic model. Okay, so I will start wrapping it up. We feel that this optimization, global optimization code, which actually worked with any of your favorite codes, it has interfaces to games, Gaussian, NWChem, or CP2K, OneTap, LAMPS. It can help us if you want to just simply optimize structures, but also if we want to consider models of a higher complexity. This new implementation offers several advantages, and we can, one of the issues that we have for training potential is that we often miss the higher areas in the potential energy surface. So this is one way, I think, to supplement with this missing configuration. And of course, with the integration of neural networks, we can quickly determine reaction pathways. To close, I asked an AI to create an image of Michele Parinello. So the AI has been thinking, and this is the output, in case you didn't know. Right? Anyway, the man has the smarts, but he has the moves too. Michele, happy birthday. Please keep inspiring us for many years to come. Thank you very much. We will be having a postdoctoral position open. Anybody that might be interested, or please contact me. Questions?
Thank you very much, Wanda. Mm-hmm. Questions? Comments?
They really want to get out of here.
Then we thank you, Wanda, very much.
All right, thank you.
So before I hand over the microphone to signal the end of this session, it helped us set up this beautiful event. They are Giovanni Bussi, Paolo Carloni, Alessandro Curioni, Marco De Vivo, Giulia Galli, Francesco Gervasio, Xingao Gong, Alessandro Laio, Vittorio Limongelli, Carmen Rovira, besides myself. But the crucial people here in this meeting and organizing all this have been Ali Hassan Ali and Victoria Lvova, who is not here, our secretary. They really, or maybe she is, who really spent a consistent amount of their life in this. Thank you. And of course, now it's time for concluding remarks.
Okay, this will be quick. It's basically the Poster Prize Awards. Okay. Okay. So, according to all the judges, this was a very difficult task. They were all really good posters, and so my general pop culture is really bad, and ever more so my Italian pop culture. But there's this guy, I don't know how many of you know him, Bruno somebody. He's an Italian British guy, and all the judges said, for me, they're all winners. So I was trying to think of something thoughtful, given this really rich, intellectually stimulating, scientifically rewarding conference. And so I turned again to my email exchanges with Michele. And so I sent him an email last night, and I asked him, I said, tomorrow we'll announce the file. I thought it might be fun to give each person a publication, not by you, but that you really like and that you were inspired by. So of course, he responds. And so he shared not necessarily the 5 papers, but some of the 5 topics that he has been inspired by over the years. Papers by Anissa Rahman, H.C. Anderson, Feynman path integrals, Consham theory, and Landau free energy. And so I thought I would print out some of these papers, and so each poster prize awardee gets to get one of these papers and read them. And hopefully get deeply inspired as Michele has been inspired of them. So I think, papers that Michele was inspired by must say something. So Michele, do you mind coming up so that you can award the people if they're around? I'm not sure that they're all around. So the first person is Annalisa Cardellini. Are you around, Annalisa? Or is anyone from your group here, by any chance? Ah, there you are. Okay. And so you get the paper by Weeks Chandler Anderson. Enjoy. The next person is Debarshi Banerjee, inferring causality from molecular dynamic simulations. And you get self-consistent equations, including exchange and correlation effects. Enjoy. The third person is Mani Young. I think she had to leave, right? Is anyone from her group here, by any chance?
Umberto.
Umberto, perfect. Umberto, you're going to come and take the prize for her. And so I could not find the paper. I need to ask Mike's help for this. By Feynman on quantum mechanics and path integrals, but please give this to her. Yeah, I need his book, which is, the fourth one is Julia Bovolenta, the interaction of hydrogen with iron under high temperature and pressure. Julia. She left. Okay. You again. So you have some good bedtime reading tonight. This is on the theory of superconductivity. And then the final one goes to Francisco Vieira on probing excited state dynamics and conical dissection, pump probe X-ray spectroscopy in non-aromatic molecules. And you get, are you here, Francisco? There you are. Perfect. This is there you go. No, there you go.
Oh, yeah,
yes.
I have to do it.
So, you have to bless it. And this is one of my favorite papers, by the way, on by Anissa Rahman. So, anyway. Okay, thank you very much. That's it for the poster session. Mike Klein. Thank you. Mike.
Check this one, just this one.
Yeah.
See, Feynman didn't write many papers. Other people wrote books.
Here you go.
Okay. So I realize I'm between you and your airplanes mostly, so try not to be too long, but I have a couple of points I would like to make. Ario already thanked the organizers, so I can move on. Thanks for having me here. So just a few words. It's been a pleasure to come back to Trieste. I was here for Coloni's birthday recently, but apart from that, I'd probably been away too long. I didn't get a chance to get Storico Nero, so it's a strange visit, deprived of local grappas. We recognize Michele's incredible exemplary career as both a scholar and a mentor, and we saw clearly from the meeting both aspects of that. The other thing I would like to focus on, it's half a century of highly original and creative work, which is still continuing. Congratulations for that. I mentioned in my earlier remarks, I think that we met certainly 40 years ago in a number of events in that era. But in my dinner remarks, I selected from a bunch of papers from the 1970s, which satisfy this 50-year window I was asking about. And I realized I actually forgot some, and I want to go and elaborate on that. 50 years ago, I was interested in molecular dynamics and Monte Carlo of alkali metals. And I've highlighted a paper here that came out in 1976 with my colleagues at the National Research Council in Ottawa, Canada, where I was at the time, on the properties of sodium. Then I discovered, looking through again Michele's list of papers in the 1970s, that he had a publication in the same volume of the journal dealing with alkali metals. So who would have guessed, and I only just realized this, that literally 50 years ago this month, we were both working on alkali metals. Who would have known that? And here are the papers, and you can look at the dates. And indeed, this is 1975 when these things were submitted. So this doesn't really qualify as a meeting. However, if you ask AI, it came back with this idea that this was a close encounter of the second kind, where there is tangible evidence that we were working on the same things at the same time, but at different places. So that doesn't really count, but it's 50 years ago. But then I thought about this. Is this a half a century of quantum entanglement, Michele? So, you know, I didn't realize until literally I was preparing these slides that this coincidence had happened, but it did. What about the third kind? So again, if you get help from Google, ask AI, there has to be an animated entity present. So I'll return to the slides I showed earlier. That was at 20 years of MD, where we honored our teacher, Anis. Here was the gathering, and I showed this slide, and I remarked that 3 of the people in attendance in that meeting already have Nobel Prizes. And however, we were both there, and here's a shot that contains both of us. So we really were at the same place at the same time. So that's a close encounter of the third kind. So I just wanted to get that out there, that half a century ago we were actually doing similar things. So I was asked to say a few words about the future, and are we witnessing AI taking over the world? I can't really answer that. But in the narrower world of material science, which occupies me mostly these days, this question is debated. So a paper came out a couple of years ago from the Google mob. The whole force of Google, DeepMind and Google Research, published a paper in Nature. And I've underlined a few remarks there that I say are very bold. They say that their methods have enabled the discovery of 2 million structures. And they say This is the expansion of an order of magnitude in stable materials known to humanity. That is an incredible statement. To have the you-know-whats, to actually put that in print with your name attached to it, requires some, maybe that's a qualification to work at Google. So the other, just mind-boggling. So actually, was it written by a human, or did they go to ChatGPT to write this? I'll leave you to make your own decision on that. However, two good friends of mine both decided this was not going to escape their attention. So they wrote a paper about a paper. This is the paper, you can look it up. And I've underlined in red there, we examined the claims of this work, unfortunately find scant evidence for compounds that fulfill the trifecta of novelty, credibility, and utility. That's a pretty damning statement. So I thought I'd analyze that a little bit more, especially for any younger people in the room. So they take the trouble, these two great material scientists, to define what is a compound first. And a compound is a novel composition of matter with known structure types, or it could be a completely new. What's the second point? They have a claim of almost 400,000 novel compositions. And according to Tony and Ram, almost all of these exist in the crystal database, if a human looks at the crystal database. And they say that in the inorganic world, Pauling's fifth rule of parsimony, in other words, nature was very modest. If it found something that worked, it used it. So these tetrahedra and octahedra are a recurrent theme in inorganic materials. The third one, which is this outrageous claim, an order of magnitude expansion in stable materials known to humanity. And they've got the statement here, a compound can be called a material if it exhibits some functionality and therefore has potential utility. Since no functionality is demonstrated for any of these 400,000 compounds, they cannot be regarded as materials. So, sorry to be pedagogical about this, but somehow this escaped the attention of referees. So I just say again, if you're going to call something a material as opposed to a compound, it should have some utility. All right, so enough of that. I thought just to tell you, just because it has the name of Google on it, you should have the same skepticism of any one of your other colleagues that would say something so outrageous that 2 million compounds have been discovered beyond human imagination. Well, it turns out, I don't have the time to go into great detail, but some of the compounds they were proposing are radioactive. And, and let's not even worry about the lifetime of the material. If you could be imagining a use, particularly if you lived in a national lab, would you walk down the corridor? So, anyway, I just want to say enough already. So I just want to, has this been a veritable love fest? Do people agree? Yes? I am thrilled that I was here. I think richly deserved. We thank the organizers already and we've applauded, so that's what I was going to do. I was asked to speculate a bit about the future. I'm not really the best person to do that. In the last 4 or 5 years, I've mostly been living in the past, if you heard my talks, I think. When you get to my age, you have less of the future to worry about, but there's a lot of the past. So most of my time is spent reliving some of the great things that happened and went by me too quickly at the time. But I can ask, can we learn from the past? And I think it's abundantly clear from this meeting, it would profit all of us to go back and look at some of Michaela's papers from a little while ago. I mean, a decade is an arbitrary number, but I will explain why in a couple more slides. The other thing is that if you see some interesting works back there that you're not already working on. Perhaps it's time you changed and started working on them. It's going to be my message. So what about machine learning? That's a beautiful example, this paper, Baylor and Michele, that came out. It has 5,000 citations. It's a great paper under any measure. And you know it. It's foundational. And this conference here demonstrates why. But for the first decade, it was hardly noticed, if you look at the scholar. So now it's reached 1,000 papers, citations a year, so which means it's going to do very, very well. But it took 10 years to reach 100 citations, which is not normal for a home run. I mean, Michele has other papers that did reach. So I'm saying here that when a paper reaches 100 citations a year, it's really arrived and is a significant work. This was a sleeper that eventually made it. But here's a tsunami. This was not a sleeper at all. So it's now at 3,000 citations a year, and this is recognized not just by me, obviously, 3,000 people a year are citing it. And it was selected by the Journal of Chemical Physics of one of the 90 papers that they highlighted to celebrate 90 years of the journal. So that's a great work. So I did a quick look to prepare this slide, and I found a couple of papers that have very few citations on the scale of Michele. I thought I would just highlight them. Here's one. After hearing the talk by Andrea about needing free energy methods, this is a paper that has very few citations, but it's applying a new method, which they say will be widely used. So those of you interested in free energy methods perhaps should look at this paper. And there's another paper which doesn't have many citations, which looks intriguing to me, and again, I highlight that. And so maybe in 5 years' time, we'll see if anything much happened with these papers. So again, this is important. And my last message to anybody that has a connection with people living in Stockholm, I would like to send a message that say that we personally enthusiastically support for Michele for Nobel Prize in Chemistry, and in October we'll know whether it works this year or not. So I'm going to say that's the final word. Goodbye to everybody, safe travels. Let's meet again for Michele Paranello at 85. Wherever you're all going, happy trails, safe travels above all, and that's all I have to say. Thank you.